So in this video, we are going to walk through this document, which is named a Hearing the Tour of RISC-V, which is prepared by TA Chun-Myung Park of this class. And in this tutorial of the RISC-V assembly, you're going to study the assembly language itself and the ABI or application binary interface of the RISC-V architecture. So all these examples that are here are compiled from C by a compiler, and you can compile a C program. For example, represented here by clang target RISC-V blah blah, and the architecture should be RISC-V with 64-bit general purpose architecture and blah blah, and then you can get the result of this RISC-V assembly. And all this document is consisting of the examples of C programs and their corresponding RISC-V assembly programs. And you can see all the examples at this site, gutbolt blah blah. And here is the example. And you can see that, oh, these programs are compiled to somewhere here. And this function, this main function is compiled to here. So, and this line is compiled to here, and this line is compiled to here, and this line is compiled to here. So you can see the correspondence between the C programs and the assembly programs in this site. And you can just go to gutbolt.org and you can select C here, and you can select the RISC-V blah blah clang here, and see the result of the compilation of the C programs into a RISC-V 64-bit architectures by clang. And this document is basically consisting of all the C programs and assembly programs that are compiled from this, and all the examples are residing in this homepage. Oh, you can reach this document by clicking some link in the slide. In the slide, there is a link to the RISC-V introduction by the TA Chun-Myung, and you can just click it and get this document. And okay, this is basically the introduction of this document, and let's go one by one of each concept in the C programs and how they can be compiled to assembly programs. The first thing to compile is global variables. So there are a few global variable declarations like a character, gchar equals to 1. So it is a global variable, gchar, of type character, and it is initialized with the value 1. And this is translated basically to this, which means that gchar is a symbol that is residing in the assembly, and it has the size of a byte, and it is initialized with the value 1. So this is basically declaring a symbol, a new symbol in the global address space, and its size is byte and its initial value is 1. So the same thing happens for all the other types as well. gshort is a half word. Here the word means 4 bytes in the assembly programs. So let's say this is a convention that is held by the RISC-V and other assembly programs. And half means half words, and that means 2 bytes. And this is saying that gshort is another symbol which has the size 2 bytes, and the initial value of this is 1. Integer is one word, which means it is 4 bytes. So C integer is 4 bytes in this architecture. So we are going to translate this integer gint into a word. So this is 4 bytes, and this is going to be initialized with a 1. And this long is translated to what is called quad. It is going to be 8 bytes basically. So this is going to be represented as 8-byte representation of an integer. And glong is another symbol who is 8 bytes, and it is going to be initialized with the value 1. Float is 4 bytes, and its initial value is a little bit complicated, but it is just a byte representations of this value 10f. It is a floating point number 1, and this is in bytes represented as 0x blah 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 blah. So this is 4 bytes. This is 1 byte, right? This is the first byte. This is the second byte, third and fifth byte of the global variable gplot. Double is 16 bytes long. I mean 8 bytes long data structure, and its initial value is blah blah blah, which is the byte representations of this GW. Double is also a new symbol whose size is 8 bytes and whose initialized value is this. So this 1.0 is byte represented as this. That's the reason why this is translated into this. So what you need to do is translating all these 6 lines into such a thing like this. So the most difficult part will be translating the bit patterns of these initializers. So you need to convert these initializers into bit patterns, but it will not be very difficult. You can just use RISC functions to convert it. Anyway, this is the simplest thing. The simplest thing is translating variables into some symbols and some data. And let's move on to functions. So here is a simple function. So here gint is 1, and it is somewhere translated into a word. It is a 4-byte data structure, and its initial value is 1. And we are going to also translate a function here, a main function, into a symbol. Main is a symbol, so we are going to translate it as a global symbol, main. And it is doing a very simple thing. It is assigning a value to a local variable, and it is returning the global variable plus local variable as a result of this function. So let's see how this is translated into assembly. The first thing to do in this main function is first decrementing the stack pointer. So this add means that this SP should be SP plus minus 32. That means the SP register is decremented by 32. Here, SP stands for a stack pointer in the assembly. So it is pointing to the stack in the execution of the program. Right? So stack, if you are not aware of stack in this context, please search for stack in the program. So it is not data structure stack. It is system programming concept stack. So if you're not aware of this, please read some documents in the Wikipedia or watch some videos from systems programming courses. They explain the stack pointer very well. Okay, so the first thing to do is decrementing the stack. That is for preparing the locations, memory locations for a backup. So you're going to back up the return address and some coli save registers from the registers into memory, like this. So we have 32 bytes backup space, and the first thing to do is storing RA, which stands for the return address of the caller. So some function called this main function, right? And the RA was the return address of the caller, and we are going to store this RA value into the stack. So we resolve the stack space, and this 24 SP means that 24 plus SP basically. So we are preparing for 32 bytes, and we are writing 8 bytes of this array into the last part of the stack, which was just preserved in this decrement action. And we are also backing up the value of this S0 to the SP plus 16, which is also the backup space that is preserved in the in the new area that is created here. And we are going to calculate SP plus 32, which is the original stack pointer, which was just before the calling this function. So this is S0 should be the caller's stack pointer. SP is the callee main's stack pointer now at this point of time. Okay, so far so good. We preserved some spec space and we backed up some register values into the stack space. So this is what was going on here. And we are now going to calculate this addition here. And we are going to prepare for the return value. So A0 is meant to be the return value. So every function returns a value, and that value is by default stored in this register A0. So A0 will contain the result G plus L that is calculated by here. And at the beginning, it is initialized with the value 0. And this A0 value will be stored in S0 minus 20. That is the stack space that is preserved here. So this is writing some value to the spec space. This is writing some value to another spec space, disjoint stack place. And this is also storing some value to a still disjoint stack place. So this and this and this are all disjoint stack spaces. We are actively storing the value 0, which was initialized here, to the new stack space here. Okay, so far so good. And now we are declaring a local register, local variable here. And we are going to get it by 0 plus 1. So this A0 will be the value of the addition of 0 plus 1. Here, I means the immediate. So this is the immediate value, not register. It is the value. That's the reason why this is called add immediate. It is adding a register and an immediate value 1 and store the result to this A1. So that's the meaning of this instruction. So as a result, A0 gets 1 after this instruction. Okay, now we are going to store the value, a word, A0 to this location. This is also disjoint from all the stack places that is preserved here. Is this A0, which is 1, is stored in this stack place. So that means that this local variable lint is allocated in the stack at this point of time, at this place. S0 minus 24 is a stack place for this local variable. And it is going to be 1, and that's the reason why we are calculating 1 and then storing the value 1 to this location. Okay, so far so good. Now we are going to load from this G here, and the G is a pointer basically. G int is a pointer to the location that is allocated here. This is a symbol that is representing a memory location that is stored with a word, which is initialized with 1. And its name is gint. And this to instruction is going to load the address of gint into A0. So just please memorize the pattern here. It is going to load the location of gint into A0. So for more information, please just go to the references and see what's going on there. So this is, at the high level, this is loading the higher bits of this gint to A0, and this is loading the lower bits of gint into A0. But the details will be explained in the other slides. So for the purpose of this homework, And for the purpose of KAIST construction, just please memorize it. So it is two instructions will load the memory location of gint into A0. Okay, so far so good. And here we are going to load the value S0 minus 24 into A1. So that means that L int was allocated here. S0 minus 24 is containing the value L int. And here we are loading a word. LW means load a word from this location into A1. That means A1 will be the value of this L int. And as these two instructions will load the value of this G int into A0, this instruction add word, which means A0 plus A1 should be assigned to A0. That means that A0 will contain the value G int plus L int, because A0 was the G int and A1 was the value of L int, and each addition will be the return value. So far so good. And A0 is meant to be the return value. So we can just return. We can just return by storing the value to A0 and return here. But before returning to the caller, we need to somehow restore the stack. So here, at this point of time, we backed up some locations, and we backed up some registers, and then we decremented some the stack pointer to reserve some space. And we need to do exactly the opposite. We need to restore the backup value. So here, the S0 was backed up here. So we are going to load it to S0. And RA was stored here as a backup. So we need to restore from SP plus 24 into the return address. And furthermore, we are going to restore the stack pointer by adding 32 to stack pointer, and then return. And we don't need to specify the return value because A0 is implicitly meant to be the return value of this function. So it is specified by the ABI. A0 is the return value. So overall, this is calculating, this is corresponding to this function, which is the main function, which is allocating a local variable and doing some addition and then return value. And this is translated into stack preparation and register allocation, and then actual addition, and then stack restoring. After that, the return value is returned. So this is basically what's going on in the compilation of this simple program into the RISC-V assembly. So you can interactively work on the things like this. So this is a main function, and you can go to here and see what's going on there. So this is simpler than what was presented here. Here we are going to use some stack, but here it doesn't use it. But if you don't optimize at all, then we are going to see more instructions from the main function that is corresponding to the lines here. So here, stack is decremented. And as well, here, the stack is decremented. And so on, so on, and so on. And if you optimize it with the optimization flags, then many of the codes will be elided because most of them are not necessary actually. But yeah, you can see what's going on there by changing the flags and see how to compile, how to naively compile this function into the RISC-V assembly. Okay, so far so good. And let's move on to the next example, which is a function that is calculating addition of integers and addition of floating points. So here, integer is a function, and here we are not going to decrement and increment the stack pointers because it is a very simple function, and we don't need to do that. The arguments are assumed to be are assumed to be given by the caller in A0 and A1 here. It is a convention of the calling convention that is mandated by the ABI. So this ABI is specifying how to interact with other functions inside assemblies, and that convention mandates that these two arguments should be given in A0 and A1. Okay, so far so good. And this is adding two words, A0 and A1, and assigning it to A0. And A0 is meant to be the register for the return value. So, and as a result, we are just going to return it. So that's simple. That's just one of the simplest function which can be presented in RISC-V. And here is another function, floating point, which is given two floating points and calculate the addition of them and returning the values here. And here it is a little bit more complicated than integer cases, because in order to perform floating point addition, we need to move those register values into the special registers that are dedicated to floating points. So this FT0 is the zeroth floating point register, and this is the 1th floating point register. And you are going to move a word to floating point from the word A1 to the floating point FT0. And also, you're going to move a word A0 to the floating point register FT1. And you're going to add it. And you're going to add FT1 plus FT0 and move it to FT0. And you're moving back this FT0 to A0 by using the reverse instruction here. This is floating point move from word to floating point registers. And this is floating point move from floating point registers into the word registers. And A0 will get the result of this addition. And by returning it, we are implicitly returning the addition of these two floating points. So that's the what's going on in this function, the floating point function, adding two floating points. Okay, so far so good. And probably I didn't explain here, but you can see that all these registers A0 to A0, A1, A2, blah blah, and RA and S0 are all 8 bytes because it is 64-bit architecture. And FT0 registers are also 8 bytes, which can hold the double types. But we are only converting word here, so that's the reason why we are converting an integer, floating point, which consists of 4 bytes, to a floating point. So W means 4 bytes, and we are converting 4-byte floating point into the floating point registers. So while A0 can contain 8 bytes, we are only converting 4 bytes. That's the key of this word W. Okay, so far so good. These are explaining how the arguments are passed and how return values are passed and how to do floating point addition like this. And let's move on to the next topic, which is control flows. And here is one of the simplest program here. So it is looping infinitely. It is a while loop that doesn't terminate at all. How this is represented? So at this point of time, this is a symbol, and this is also a symbol, and it is a temporary symbol that is the zeroth basic blocks, the first instruction, like so. Okay, and if someone is jumping to this function, then the program counter will point to this point. And at this point of time, we are going to execute this instruction, which is jumping to this label. This label is bud itself. So the meaning of this is that if the program counter is here, we are going to jump to this label, which is itself again. So the program semantics of this is that jumping to itself, jumping to itself, jumping to itself, etc., infinitely. That's exactly matching with the semantics of this C loop. It is, if the program counter is here, it is jumping to here, blah, 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 without any breakage. It is looping again. The same thing happens here, basically. Okay, that is describing two things. The first one is the labels, and the second one is this jump instruction. It can be given with the label, and if this label is given, it is immediately jumping to this label. Okay, so far so good. And let's move on to the conditional jump here. So this is given 3 values: cont, true, false, and this will be A0, and this will be A1, and this will be A2. And this will be compared with 0, basically. So at the beginning of this function, A0, which contains the value of cont, is compared with 0 here. So A0 is compared to Z, and if it is equal to 0, then it is going to jump to this label, which resides in here. So this is basically a conditional jump. If A0's value is 0, we are going to jump to this. Then if it is the case, we are going to assign A2 to A0, and A2 is returned. So the false value will be returned here. Otherwise, if it is non-zero, then we need to go to the true branch. And at this point of time, A1 is assigned to A2, and A2 is again assigned to A0. So overall, if it is non-zero, then these 2 instructions are executed, and in turn, A1's value will be assigned to A0. That means true will be assigned to the A0, the return value. So in a sense, if the condition is non-zero, then the true value will be at the return address, return value register, and this return value register will be returned at this point of time. So that's basically what happens in this series of instructions. And the most important point here is the conditional jump here. Depending on the value of this A0, if it is 0, then it is going to this, and if it's non-zero, then it will continue to execute the next instruction. Okay, so far so good. And let's move on to the function call here. Okay, and as we already discussed a little bit, a function the registers arguments are passed to A0, A1, A2, etc., and the return value will be stored at A0, right? And this is a simple function. So this is given a value, and it is immediately returning the value here. So it is very simple. A simple function can be translated into just a single instruction ret, because the given value is stored in A0, and this value is immediately returned because A0 is meant to be also the return value. So by returning immediately, we are just saying that the first argument will be the return value of this function. And let's move on to the next function, which is the main function, which is just returning simple one. So we are going to call a function here. So we are going to call a function, but we need to somehow prepare for the registers and other things. The first thing to do is, as we discussed in the previous example, preparing for a stack. We are reserving 16 bytes of stack space. And we are going to store the return address into this point, this stack point. The array is backed up here, and it will be restored here, and the stack will be restored here as well, and we're going to return. So you can think of it as a template of the function. You reserve the stack place, and you back up the return address, and here you're going to restore it and back up restore the stack place, and then return. And all the interesting will be happening between this preparation and this epilogue. So here we are going to assign 1 to A0 because the return, the first argument will be 1 for this function, and we call the simple function. Then A0 will be the return value. And we are going to typecast this long to integer because we are given long, but we need to return an integer. Then there will be the instruction. So this will be assigned the extension for word, and we need to apply this function to itself to typecast a long to integer. So if you're curious about which instruction should be used for which typecast, you can just go to gopult and implement the typecast function and how Clang compiles this into the RISC-V assembly. You can just exactly mimic what Clangs do, what Clang or GCC does. So this is also derived from what Clang does. If you you convert long to integer, then Clang does so, then we can just mimic them without understanding the meaning of this instruction. And as I said, we are going to restore the stack and return. That's all. And all the interesting thing happens here. Setting up the argument, calling a function, and typecasting the result. And this is the epilogue and the prologue of the functions. This is a little bit more complicated example, which is very, very nice. This is given 9 argument and adding all the things and returning the value. So this is basically the what's happening here. And we are basically using A0 as an accumulator. A0 will be A0 plus A1, and it is added by A2, A3, blah, 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 and A6 and A7. So far, so good. But A7 is corresponding to P7. And the ABI of RISC-V says that you can hold up to 8 arguments inside registers, A0 to A7. A8 is not an argument, so P8 should be stored somewhere else. So that is the stack pointer here. So when you call a function like complex, you need to prepare for the last argument here, P8, into the stack. So this stack pointer will hold the value of this P8. And as a result, we are going to load the value of this into T0. And here T stands for the temporary. The T0 contains temporarily the value of P8 here. And at the end of this execution, you're going to add A0 to with T0, which contains the value of this P8, and return the value here. And as a result, we are going to sum P0 to P7 and, in addition, P8 by using this instruction. So as a result, A0 will contain the summation of all the arguments at the time of this return. Okay, so far so good. And let's see how to implement the stack here. How to implement the main function here. So here we are preparing for the stack place, and we are going to use 16 bytes of the stack space, and then the return address will be stored here. That's so far so good. And the only thing we should do is calling a complex function. So we are setting up the registers here. But as I said, the last argument cannot be stored on the register. So it should be stored in the stack place. So that's the reason why we are calculating, we are setting T0 to be 9, which is the last argument. And this T0 will be stored as at this place. So as a result, this SP0 will contain the last argument. And after we call the complex, inside the complex, if we load from this as SP0, then it will be the last argument, which is 9 at this point of time. And blah blah, and it calculates the summation of all the arguments, and it returns the value, and it typecasts, and then restore the stack, and then return. It's simple. So the one thing you should know about this is that, registers can hold up to 8 arguments, and all the remaining arguments should be placed in the stack. And you need to see what's going on by actually compiling this kind of functions to see how to place the arguments inside the stack. And also there's another point to notice is that it is storing the return address here. So we need to store the return address only if we are calling another function inside this function, because this calling instruction somehow changes the value of this array. On the other hand, complex function doesn't call into another function. So that's the reason why we don't need to store or back up the value of this array into the stack place. So this doesn't call another function, so there's no need to back up the array. And it calls another function. That's the reason why it needs to back up the value of this return address. Okay, so far so good. And here is the last topic of this video, which is the struct type. And here is a struct which consists of 2 long types. Here the long means that 8 bytes, and this is overall 16 bytes. And it is regarded as small by the RISC-V ABI. And so let me see how things are going on with this struct inside this for these arguments basically. So this is the main function, and it is going to do some things to prepare for the struct value. So okay. So this is okay. So this is the constant value that is consisting of 2 long types, and this is the variable declaration, which is a constant value which contains 2 values, 1 and 2. So this is basically the value here. And when you are storing a value to A, and we are effectively loading these values into 2 registers, A0 and A1. Because A0 is 8 byte and A1 is 8 byte, collectively they can store the value of this struct. So A0 and A1 are, after these 3 lines of code, they can contain the value of this 16 bytes constant. And now we are storing this value into the stack basically, because this A is allocated in this stack place. That's the reason why we are so the last 8 bytes will be going to return address, and the next 16 byte will be going to the variable A. So A's value will be located in the stack. Okay, and when we are calling the sync function and sending the address of A to the caller, this function, then we are going to just send the pointer to this a value, right? So that's the reason why a0 will get sp plus 8, because it points to the value of this this constant that is stored in this a. So it is pointing to the pointer to a, and the pointer to a is given as an argument to this function, and we call the function like this. Okay, so far so good. And the next line will be assigning another struct R by calling a foo. So we are setting up the values again. We are setting up the a1 and a0. So they will point to the first argument, which is going to be a as a struct. And we call the foo function. So the moral of the story is that if the argument here is 16 bytes long, then it cannot be stored in one registers. So that's the reason why we store the values into two registers, a0 and a1. And collectively, they will mean the value of this argument a. And, okay, so far so good. So far so good. And okay, then we are loading the values of a into a2 and a3. And similarly, a0 and a1 will have the return value, which is 16 bytes long of type this struct a. That's the reason why we don't touch a0 and a1, because they will contain r, which is the return value here. And we are calculating all the values here. And a0 and a1 will have m1 and m2 of r. And we are loading a's m1 and m2 into a2 and a3. And after adding all the values here, a0 will contain the value of the return value here. So r's m1 and m2 plus a's m1 and m2. And then we are going to do backup. We are going to restore the stack and return a0, which will contain the summation of all the things. Okay, the moral of the story is that if the struct has a size of less than or equal to 16 bytes, then they will be split into two registers so that they can be fit into the registers. So that's the story. And here, even though there are only one argument, it is represented by two registers because its size is 16 bytes, and return value is the same thing. Even though it has one return value, a0 and a1 will collectively contain the return value of this function. So you need to mimic actually what clangs do or what GCCs do for this argument passing. But if the struct has a very big type, then you are not going to do it for the things. I mean, if this struct is very big, you cannot split them into multiple registers, because even though we split them, there are so many registers to be used for passing this value. If that is the case, we are just going to use the pointer to this value. We are effectively converting this function into function argument into the pointer to the big. And we prepare for this argument inside the stack, and we are going to pass just the pointer instead of the value itself. So but that's basically explain details here. So this argument will be converted into pointers. So if there is a too big argument, it is going to be converted to a pointer. And similarly, if the return value is too big, it is also going to be converted to the pointer, which will contain the pointer to the return value. And this foo function will write the value of this return value into this pointer. So this is basically explains such a thing. So you can read it, and you can. I am quite sure that you can understand the instructions here if you follow the previous examples well. Okay, so far we saw a few examples of translation of C programs into RISC-V programs, and I hope you can mimic what I did for your homework. So if you need to translate some concept or some program of IR, then you compile the corresponding C code into the RISC-V by using GCC or Clang or Compiler Explorer, then see how you should translate and do translate as instructed by the compilers. And if you want to study the calling conventions or the instruction set architecture itself, then you can read these instructions here. The specification contains not only the assemblies but also calling conventions and ABIs. And you can also execute these assemblies by following this instruction. So you can basically install the QEMU, which is the emulator for binaries, and you can compile these binaries into, you can compile these assemblies into binary and execute those binaries on top of these emulators. So these instructions are written here. And if you don't want to install your compiler but still want to see the RISC-V compilation results of C programs, then you can go to Godbolt and use a compiler there. You can just write C programs and do C whatever is generated from the this C program. So that's basically everything you should know about the RISC-V assembly to do the homework 7, which is assembly generation.